All right, so we're going to get started. Welcome everybody to the second day of NANOG, and look forward to another exciting round of things going on. I want to remind everybody that's here to go ahead and fill out the surveys, the daily surveys. In fact, who did that for yesterday, Tuesday? Is today, who did Monday? Anyone? I did. There are prizes for those that do that, obviously. We do those every day, so later today there'll be a prize awarded for survey. Picked randomly, of course. Also want to remind everybody that limit the amount of sidebar conversations because the amount of noise that it generates within the room. And if you do go outside the doors to have a private conversation, if you could be further away from the doors to reduce the amount of noise coming in. We had a lot of feedback from that yesterday as well. The last comment I'd like to make is lightning talks. We have a few of those for today. We're working on additional ones for tomorrow, but if there are more ideas, more abstracts, we would love to see some new ideas come in as we vote those in for Wednesday. So any additional thoughts for lightning talks? Again, 10 minutes or less, those would be great. We'd really appreciate it. And with that, I want to get started with the current track for this morning on DNS. Dwayne is in with a team of 5 people, so we'll have 5 people set at 15-minute intervals to be able to give you different segments of what's going on in DNS. It's a very important thing for NANOG from both an operational experience as well as security, as well as the well-being of the organization in general. So Dwayne, go ahead and come up. Thanks, appreciate it. So this is your cue to be able to go and move forward and back on the side. So you just turn this on and then
the big green button?
Yep.
All right. Thanks. So yeah, we've got 5 presenters. We're each going to try to limit ourselves to 15 minutes each. We've got a wide variety of talks today. The first talk will be about DNS measurements from root and TLD authoritative servers. And that'll be followed by a talk about using looking glass techniques to do some diagnostics against DNS issues. And then we'll hear about using DNS to do some device identification with focus on Internet of Things. And then lastly, a couple of talks about the root zone DNSSEC changes upcoming. One about the zone signing key and one about the key signing key. So to start off, I'd like to welcome Kazunori Fujiwara up to the stage from JPRS to talk about some trends in DNS at root and .jp. This will advance the slide.
Good morning. I'm Kazunori Fujiwara from JPRS. Today I will talk about DNS query trends seen at root and JP. And are DNS query increasing? How much queries does each IP address send to root TLD? Is IP version 6 deployed? Is DNSSEC deployed? To evaluate, I analyze the 2 data sets. One is DNSORG's root dataset. DITL is a large-scale data collection project undertaken by CADA and DNSORG every year. 48 hours packet capture at root DNS servers. And the other data is JP dataset. JPS collects packet captures of all JP DNS servers around the same time as DNSORG's DITL event. These are my interest of the evaluation. Number of queries, number of query source addresses, query ratio of IP version 6, EDNS0, DNSSEC OK, ratio of IP version 6 addresses, ratio of IP addresses that send EDNS0, DNSSEC OK, root DNS key queries, and analyzed by countries using Maxmind's jailbreak-free country database. And this graph shows collected queries at root DITL dataset, 48 hours, average queries per second. This graph shows increasing tendency, however, 5 times increase in these 8 years, slower than content size. And this graph shows number of queries from each IP addresses at root 48 hours. Horizontal axis shows ranking of each IP address, and vertical axis shows number of queries from each IP address. This graph shows the same tendency by years. Why they send over 1 million queries to root in 2 days? And I analyzed that some of them comes from type or unexisting TLD queries and implementation bugs. And there are 2 types of storage data in this year at root. One is heavy query senders. Number one address send 235 million queries in 48 hours. 1,364 queries per second average. And number two send 100 million queries in 2 days, about 600 queries per second average. And both number one and number two send recursion desired of with EDNS 0 opt-RR DO bit set, and 99% of queries is existing TLD queries and various query names. However, the addresses doesn't seem to use cache. And number 3 address sent 95 million queries in 2 days, about 555 queries per second. And the address sent recursion desired of with EDNS 0 opt-RR DO bit set. However, the address sent a2m.root-servers-net quad A and A6 queries only. And the other type of storage data is IP addresses that send RD bit set only. RD bit shows recursion desired, set by stub resolvers. Recent full service resolvers don't set RD bit. 60% of IP addresses send RD bit set query only in this year. They may come from misconfigured hosts or bots. The ratio is higher than previous, 20% last year. And analyzing only RD0, RD off queries may be useful. This graph shows ratio of RD bit set only queries at root. Ratio of RD bit set RD1 query is small and relatively stable, about 4% in this year. However, ratio of IP addresses that send RD bit set query only is not stable and very high, 62% in this year. And RD bit set query may come from stub resolvers or careless bots or careless measurements for root DNS servers, and these queries may not show internet status. Following evaluation are the graphs that excluded IP addresses that send RD bit set query only. Ratio of IP addresses that send RD bit set only is 1 or 2% at JP DNS servers, smaller than at root. This graph shows ratio of RD bit set by country this year at root. Ratio of United States IP address RD bit set only address is about 70%, slightly higher than average, and 52% of Canadian addresses send RD bit set only query only, smaller than average, and 96% of China address, 91% of Korean addresses send RD bit set only query. And the table shows query source ranking by countries at root this year. Ratio of US IP addresses is very high, 32%, And US and China addresses generate 23% and 20% of root queries, very high ratio. And number of queries divided by number of IP addresses high at some countries. For example, China, Taiwan, Turkey. And this table shows query source ranking by countries at JP this year. IP addresses in JP generates 38% of JP queries, and this ratio is reasonable. And IP addresses in US generate 25% of JP queries, and US uses largest number of IP addresses to resolve. And this graph shows number of queries from each IP address per countries in root this year. Strange IP addresses exist on all countries. Top query generators are Brazilian addresses this year. And the number of queries from each IP address per country in JP, and this graph shows number of queries from each IP address per countries in JP this year. IP addresses in Japan generate many, however, not significant queries to JP. JPTLs is well used from Japan, and JP zone has about 1.4 million delegations and one day TTL. Busy resolvers may send 2.8 million queries in 2 days. Top query senders are from US and Germany. This graph shows ratio of quad day queries. IP version 6 query, quad day query is well used and almost stable, about 17%. Ratio of IP addresses that send quad day queries is large, about 48% at root, 43% at JP. The reason of the increase is that most of clients' applications and OSs send both A and quad day queries. These quad day queries may be hidden by query name minimization. Excluding addresses that send RDBit set queries only hide irregular decrease of ratio of IP addresses that send quad day queries at root, light blue line and deep blue line. This graph shows ratio of IP version 6 queries in 48 hours. IP version 6 transport is well used, about 7% at root, 12% at JP. Ratio of IP addresses has been increased, currently 5% at both root and JP. Excluding addresses that send RDBit set query only hide irregular decrease of ratio of IP version 6 addresses at root, light blue line. IP version 6 usage may be still increasing or stable. This graph shows ratio of ETNS DNS OK queries. About 70 or 80% of all queries have ETNS 0 and DO bit set. The query sources know DNSSEC, at least software support DNSSEC. And this graph shows ratio of DNS 0 DO IP addresses. DNSSEC protocol support in full service resolvers is well deployed. 70% of IP addresses at both root and JP. Excluding addresses that send RDBit set query only hides irregular decrease of IP addresses ratio, light blue line and dark line. And this graph shows DNSSEC validator at root and JP. DNSSEC validators send root DNS key query every day. Blue line shows ratio of IP addresses which send root DNS key query about 6 or 9%, and red line shows ratio of IP addresses which send root DNS key queries except RDBit set only addresses, and the line shows currently about 16%, and DNSSEC validators send each JP domain name DS query every 900 or 7,200 minutes. And dark line shows the ratio of IP address which send domain name JPDS queries, currently 9.7%. And the ratio of probable DNSSEC validators may be 9.7 or 16%. These are findings. Queries to root DNS servers are increasing, 5 times increased in 8 years. And some addresses generate strangely many queries. Some hosts send over 100 million queries in 2 days, and 100,000 addresses send over 1 million queries in 2 days. And IP version 6 query type quad is well used, almost stable, 17%. IP version 6 transport is well used, 7% at root, 12% at JP. Ratio of IP version 6 addresses is increased, currently 5%. Ratio of probable DNSSEC validators may be 9.7% or 16%. And the DRTL dataset may contain irregular data. We need to analyze them. Ignoring RDBit set queries is one effective idea to decrease effects of irregular non-full service resolver queries. This is, I would like to analyze analysis of strange IP addresses to find the reason of unnecessary queries, and easiness option analysis, DNSSEC IP version 6 deployment by countries, ideal new DTLD queries by countries. And that's all.
Any questions? We have a few minutes for questions. If anyone has questions for Fujiwara.
Matt Petak from Yahoo. This is great data. I'm curious, you identified 3 anomalous IPs that were generating hundreds of millions of queries. Any chance you could identify who those IPs were? If it's one of ours, we could try to see if it's a misconfiguration. It seems like it's a very strange set of outliers in the data. Or is that something we should ask you privately about afterwards?
Currently, I cannot say the address.
Okay, thank you so much.
Any other questions? Okay, thank you. Thank you very much. So next I'll invite Casey DCO up to talk about DNS diagnostics using looking glass techniques. Casey, this is your microphone, and this is your clicker. The green button.
I almost had these 2 reversed, so I'm glad. All right, so again, I'm Casey DCO. I'm with VeriSign Labs. I wanted to talk a little bit about some recent advancements in feature functionality and tools to assist with DNS diagnostics and measurement. So just to make sure we're all on the same page, this is my 1-slide DNS background. So we have, in the typical model, you have a stub resolver, which would ask questions of your recursive server, and then beginning at the root, it would ask this query and then follow referrals downward, depending on what's in its cache. Finally, when it reaches the authoritative server who sends an authoritative response, it can in turn return that response back to the stub resolver. So that is DNS in a nutshell. Now, the problem with this is the typical model, but if you look at the way things are actually deployed, oftentimes there's missing components. There's a lot in the middle between the stub resolver and the authoritative servers, and that could be there could be multiple recursive servers there, not just a single one, or in some cases, especially with, for example, the Get DNS API, you might actually have a stub resolver going out directly to authoritative servers. There may be middle boxes along the way, firewalls, NATs. You may be talking to an Anycast instance that may be different in different places. And of course, you may be talking to different authoritative servers. Then, along the way, along with the problems associated, the uncertainty with the path between a stub resolver and authoritative server, you may see some issues either with connectivity itself, okay, whether it's routing or firewalls or whatnot. You might see different latencies along the way. It's something you're trying to measure and identify problems associated with that. There may be problems blocking eDNS versions, either eDNS in general or it might be future versions, okay, which may be a future concern. Okay, there may be problems with DNS records, either because they're being stripped or because the packets are too large to get back. And then same thing with large or fragmented packets. We see problems with middle boxes there. Okay, different record types that might not be responding. The server may not be responding to certain record types. And then, of course, just general response, correctness, and consistency. What you see here doesn't match what you see here. Maybe that's expected depending on if it's a CDN or something else, but maybe you just want to know these things. Okay, so just to talk a little bit about the way things work. So that's kind of some background now associated with paths and what you're looking at. Some background with a tool that has been developed called DNS Viz. Some of you may be familiar with the web-based version. There's also a command line version, and so I'll be talking a little bit about both. And this isn't meant to be a DNS Viz overview, just to show where some vantage points can be measured from this. So the way DNS Viz typically works to do some diagnostics is that it's installed at a certain location, and then it will send queries towards the authoritative servers, diagnostic queries, over IPv4, IPv6, UDP, TCP, and it'll send special queries along the way to try and measure some diagnostic behavior. And then output this to a file in JSON format with some meta information along with it. Okay, and that's if you use DNS Viz probe with the -a. Similarly, you can get different results if you use DNS Viz probe without the -a to hit recursive servers. By default, it hits your own recursive servers. The nice thing about this is, so this is again a different vantage point from looking at the authoritative, because what really matters in the end is what's in your cache. A lot of times in terms of what you're looking for. So if you either use what's in your resolve.conf or you specify recursive servers, you can now actually see what's in your cache or what's in the cache that you have specified to see what problems there are there, what type of responses you're getting, whether it's cache poisoning or some type of misconfiguration for which you're getting failures. It might be DNSSEC related, it might be related to something else, some type of lame delegation, but the point is now you can have recursive and an authoritative view of things, and again, this goes to a JSON file output. And then there's also a web interface which you might be familiar with, which you can specify recursive servers or authoritative servers similar to the command line version that I just showed you, and that's at dnsviz.net. It's just a selection where you can, a drop down basically, where you can discover either type here. Okay, so just to show you a couple examples of how this might look differently. Now this is DNS Viz graph output. If you don't know what this means, don't worry too much about it, but I'm going to show you some different examples. So for example.com, the actual domain example.com, this is what the signed version looks like, where you can see kind of the chain of trust in DNSSEC, where the arrows are representing either hashes or signatures. Along the way, you can see when you query example.com for type CNAME, you'll see the authenticated denial of existence and some other features there. Okay, and this is what it looks like with an authoritative view. Everything looks good. Similarly, if I use one recursive server, then it may look like this, which is very similar to what you just saw on the previous slide in terms of everything looking good. However, I came across a few different views. This is a second recursive server, and provided by an open resolver service. Someone that, in this case, you are able to see that there are some problems here that are highlighted in red. You see that they're stripping DNSSEC signatures. So if you were trying to do validation and using these servers as your upstream, you wouldn't be able to do that, of course. Things are missing here. But the point here is to demonstrate that it depends on which vantage point you're looking at to do things. So if you were looking through your authoritatives, everything would look fine. If you're looking through a second recursive server, things would look fine. But when you come to this one, things look problematic. Now, in this case, things are a little bit more obvious because you can see they're stripping all signatures, and so it's somewhat easy to track down what's going on, although a visual can help with that. In this next case, this was a little bit more subtle example that came across in a lab, actually, and used this vantage point diagnostics to help with. This is the case where we were getting everything we thought we needed, except for we weren't getting signatures on the NSEC records in the authenticated denial of existence. And you may say to yourself, okay, what's this useful for? So we got some type of a DNSSEC validation failure that example.com of type C name, there was no record of type C name for this, okay. The problem with this, in this particular case, it turned out that anything including DS records, you would get authenticated denial of existence failures for validation of authenticated denial of existence. And for those of you that may not be DNSSEC aware or familiar with that, that means that any signed zone, any zone out there that is not signed, which is, there are many DNS zones that are not yet signed, then validation would not work for that, which means that you would now have a failure for any unsigned domain, and that's problematic if you're trying to use this for a production resolver. Okay, so anyway, understanding where the problems are here from different vantage points is useful. Now, you may also want a third-party vantage point to look at things, because you may like to see what someone else is seeing. And so there are various platforms out there, different access ranging from shell to API. The tests range from kind of canned queries to somewhat custom. And then, of course, like where the probes are and how you want to go about it. If you want to be able to shape your next query based on the result from the previous query, I call that sequential progressive diagnostics. So you want to determine what to do next. So you don't necessarily want the probe to do all the work. You want to be able to style that. So those are some considerations here. What I'm presenting on today is a DNS looking glass over HTTP, in which the client encapsulates requests using a JSON format, and then using an HTTP post, that information is sent to an HTTP server, okay, and included in there are the DNS message itself. So in other words, the client actually forms the message itself, so it's not the server end that's doing that, and it's also designated the server end port, so it tells the looking glass where to send the query. So this is different than just saying, hey, go look it up for me. You're actually specifying which server destination you want to go to, and you're giving it the message. So you can customize your EDNS options, you can customize your query name and type, whatever you want to put in there, you can do that. Your compression, you're basically sending it the wire message. Okay, and then you get back the response, but you also get some meta information associated with that. For example, you'll get your response time from the looking glass. You'll get, if you have problems with network connectivity, for example, you'll get some meta information associated with that, what the problem was. Okay, so in a nutshell, that's what it looks like. And there's some proof of concept code with the DNSViz source, which is open source and available at GitHub. And there's a script called digviz, which is intended to have similar behavior to ISC's dig. The point was just to provide an interface that many users are familiar with, but also to plug in some looking glass functionality. So you can see on this slide, if it's large enough for you to see, the plus LG option, which says specify a looking glass with some type of URL, excuse me. And so you can set up a looking glass. You can then use that looking glass to perform the query that you're otherwise specifying with dig, or digviz in this case. Okay, and then similarly with I'm just going to run through these fairly quickly so there's enough time. But I already mentioned the DNSViz probe. You can now specify a looking glass for DNSViz probe as well using the -u option. So you're now sending these queries through an HTTP server rather than directly. And this is for the authoritative servers, but similarly for the recursive servers, you can also go to an HTTP server first as your looking glass that will then in turn send these to the recursive server. So you can get that vantage point of the looking glass wherever it is. You've got it hosted by a third party or you're hosting it yourself on some foreign server. Now, I should mention that there isn't infrastructure. This is talking about the functionality, this talk today. Not necessarily, I'm not indicating that there's infrastructure out there where you could just plug in and use somebody else's looking glass, because it's not out there, and this is meant to talk about the technology there. And if any of you are interested in standing something up, either for the public or for DNSFiz use or for something else, feel free to let me know. Okay, so let's see. Similarly, with the web interface, there's kind of a proof of concept idea there where you can actually get the vantage point from your own browser. So typically, if you've used DNSFiz.net, the web interface, the server is actually sending the queries out, the diagnostic queries out to, when I say the server, the web server is sending the diagnostic queries out to either the authoritative server or the recursive server. But you can actually specify a third-party looking glass, either an actual third party if you've somebody set up a server, or you can do a we've developed a Java applet, nobody throw anything at me, that will act as a looking glass now, so you can send these queries directly from your client, which is actually useful, so you don't have to actually install anything, but you can still get the vantage point from your own client if that's where you're having the problems. Now, I should mention, if you go out and try this, there is maybe more, but at least one unresolved problem with this proof of concept applet, and that is you have to add an exception for HTTP, the HTTP site for DNSFiz.net to your exceptions, security exceptions in your Java config. Otherwise, it will throw some type of error. If you have questions about it, let me know later. But or if you're a Java programmer and you know something, then please share it with me, because I am not. All right. Okay, so I mentioned the applet already. And so in summary, we want to be able to make it so that you can measure and diagnose DNS from different vantage points, and there is some tool functionality we've presented today to help you do that, and hopefully this is useful. And if you have any questions, now would be the time. And I'll just mention again, feel free to look at this, both the web-based version of the site as well as the source code, which is available on GitHub, and glad to take any questions or comments offline. Great, thank you.
Yeah, thank you, Casey. So next is Yassine Naji from Georgia Tech and NetRisk. Will talk to us about DNS-based device identification. The green button.
How do I make it go backwards? The red one?
Try the red one, but no guarantees.
All right, cool. I think I'll be okay. Hey, good morning, everybody. Thanks, Dwayne. I'm Yassine. I'm a postdoc at Georgia Tech, and I'm here to talk about some passive DNS-based device identification. Most of my thesis work was using DNS to do cool things, primarily in the security space. So this is less about DNS and more using DNS to do something cool. So let's say you're an ISP and you're worried about the Internet of Things. This doesn't look like it's in log scale, but I promise it is in log scale. And this is just lots of devices that are appearing on your network. And these are light bulbs and fridges and door locks and doorbells that are on Wi-Fi for some reason. I would imagine you might want to know where these are and have a reliable, automated way of detecting when existing devices that we know about are on your network, as well as when new devices appear on your network. And you can use DNS to do this to a certain extent, and I'm going to talk about how I can do that right now. So, let's see. Green. So the main goals we want to get with this are we don't want to do it with endpoint management. So in the security space, this is a common way of, you know, when you do bring your own device in an enterprise network where I force you to install some app on your iPhone so I can make sure you're not running 8 versions ago and I can authenticate you to the network. This is obviously cumbersome because you have to, 1, know that the device exists, and 2, it has to not be a light bulb that someone has designed endpoint solution for. So the obvious thing to go with that is let's try and make this network-based. Second, we'd like this to be scalable. We want this to work at ISP scale and not a 50-person office kind of thing. And a lot of the work that we have done in our lab has been DNS-based because it's relatively easy to collect at scale and kind of summarize it. And you can do a lot of interesting things, in this case, like device identification. And second, we want it to be as automated as humanly possible. You'll see that there is probably some human in the loop here and there, but a good chunk of it is automated. And then verifying that it's correct is pretty straightforward. So we rely on machine learning to do this. So let me give you a kind of machine learning 101 crash course with the particular technique that we use here. And which is called, it's commonly used in document classification or text classification tasks. And what it's called is the vector space model, where you have a set of documents, and the documents are contained of words, and then you turn those words into an n-length vector that represents those terms. And once you have a vector like that, now machine learning becomes very easy. It's just a bunch of numbers, and now we can start crunching them. So to give you an example, here are 3 books: The Long Ships, Dune, The Little Prince, all of which are good. If you haven't read, I'd highly recommend it. And you can take a look at the actual words contained in the document. So here are the first sentences. Along the coast, the people lived together, in the week before their departure to, and once when I was 6 years old. So the easiest thing you can do is just assign a unique value for every word, and then this builds your vector. So for example, it's hard to see with the white text. I changed it pretty recently, unfortunately. But the second column, it corresponds to the word the. The first document has it twice, the second document has it once, and the third document has it 0 times. And this is more or less how you build this vector that summarizes the document. There are a handful of ways you can weight this. And this is to, you'll see the obvious problem with it. So the previous example was, it looked at the frequency of them. Obviously, if you're looking at English documents, you're going to have the word the and to and of and a be very popular. In text classification, they usually just filter these out, but there are more robust ways to handle it. And the main one for that is called inverse document frequency, which is basically the log of the ratio of the total number of documents you see in the set, and then the number of documents that that term appears in. And what this is trying to do is get specificity of the term. And if you do it again for these books, you see these words in The Long Ships, they're Vikings, they talk about ale all the time. And then in both Dune and The Little Prince, they have an almanac, but they're spelled slightly different. These are very specific terms, but they're not necessarily popular in that document. So usually what people do is the product of the term frequency and the inverse document frequency, called TF-IDF. And what this does is it tries to select terms, in this case, that are very, very common or very frequent in a document, but then are very specific to that document. So in this case, we start getting things like Orm, which is the name of the main character, or Arrakis, the planet from Dune, or Prince, Foxes and Flowers, which occur very heavily in The Little Prince, but not in the other books. Now, we do this basically, we kind of translate this technique into the DNS space, where in our case, documents are IP addresses, and the terms that make up those documents are the DNS requests that those IPs issue. And you can see what we're looking for is, for a given IP that's, say, an OS 10 box, we're looking for a domain name that's very, very unique to OS 10 and is very commonly queried by OS 10. And what this will eventually lead to is classification. So the overall process that we try and do here is, first, we try and classify all known non-IoT devices, mostly because it's very easy to get ground truth for these. So what we do is we actually collect HTTP headers, MAC address information, et cetera, to get ground truth. So I know that, well, at this time, this IP address was only one operating system, and that was OS 10. But the classification, the model we get afterwards, can be done purely on DNS traffic. And right away, we're getting some pretty good results. We get about like 90% accuracy for operating systems. And this is, since it's a 7-class problem right now, this is better than random guessing, which would be about 14%, or maybe upwards of like 20 or 30% with, if you kind of weighted it by how popular a device is. And then, I was really impressed when it was like differentiating subversions of Windows. It's pretty cool. Now with this, you can then classify everything as, okay, these are Windows boxes, these are Android things, blah, blah, blah. And then anything with a low confidence from the classifier, you can then use this same technique to do it in what's called an unsupervised case, or where you're doing clustering. And what this would allow you to do is then identify groups of machines whose DNS behavior is very, very similar. And a lot of these times this corresponds to an actual device. And yeah, that's more or less what we do here. And there's some nice benefits, but let me kind of show you some initial results. So this is, for those that are familiar in the machine learning space, this is called a confusion matrix. This is basically saying the column here at the beginning, this is like the known label for a particular internal IP, and the row represents what my classifier predicted it as. And this is kind of the result you want to see, where the diagonal are the largest numbers. This basically means, on average, I'm predicting this correctly. And usually when a false positive occurs is when the device hasn't been on the network long enough to have issued one of the queries that I know is associated with a particular device of that class. Now, one of the coolest things about doing it in the text classification way is you can basically ask, okay, so for the Android class, what are the most popular terms, or in this case, domain names, basically as a human-in-the-loop verification step to make sure everything is going okay and you're not doing things incorrectly. So for example, here are the top terms for Android, Linux, OS X, and iOS. And I've bolded and kind of highlighted some of these, so I'm going to talk about it a little bit. So down in Linux, you see ppa.launchpad.net and some things for Ubuntu. These are the ones used for apt-get in Ubuntu to basically do updates. This is something that those operating systems are going to query all the time. Android, you see play.google.apis. This is nice. OS X, there's an interesting one here. You'll notice at the end of some of these domain names, it says .lon.gatech.edu. So all these experiments were done on Georgia Tech's network, and this is the gateway for getting on the campus-wide Wi-Fi. But all this stuff before, this is like some service discovery that OS X does with MDNS responder. They basically just yell DNS queries constantly. So this is one of those things where if I were pushing this model to someone else, you would want to get rid of the lon.gatech.edu. However, all networks with OS X machines will see this weird b._dns-sd._udp. Whatever the domain that you're operating in. So it looks kind of weird, but it actually is very representative of OS X DNS behavior. iOS, you see pancake.apple.com. I think this is some emoji set that they added recently, but we found it right away, so that's kind of nice. And then Android, I bolded this settings.crashlytics.com, because this is an interesting case that I'm going to be tracking in the future, which is this was originally a tool suite only for Android crash reports for Android applications, but now it works for iOS. But because of the way we do this over time, what I expect is settings.crashlytics.com to be less and less indicative of only Android, but also indicative of OS X, which eventually it'll just kind of fall off the map because they'll be equally used by the two devices, in which case it's no longer discriminative for a particular class, so we kind of ignore it at that point. Similarly, this is it differentiating Windows 10 from 7 from 8.1, and you can kind of see, like down at the bottom, there's win8.ipv6.microsoft.com. These kind of things are allowing it to differentiate these different versions. So looking at these domain names, you might go, well, yeah, I could probably just find these on my own, and yeah, you probably could, but you run into issues where if they change all these domain names, you have to do that again, and then obviously talking earlier about all the variety of devices that will soon be appearing on our networks, it's important that there's a semi-automated or fully automated way of doing this. And if you have good ground truth label, you can more or less just let it run. But otherwise, it's easy to involve a human to make sure that metron.live.com.nsatc.net actually is something affiliated with Windows. So now I want to talk a little bit about using this same technique to do clustering to basically identify new classes of devices, which then can be modeled and used in the same way as I did for kind of like traditional OS and mobile device classification. So I built this little web app. Bear with me. I think the important part is going to be visible, but basically this does clustering and then builds a hierarchy of the clusters. and it allows me to go and investigate what are the most popular terms there. So this is on a smaller network that we have that's focused primarily on IoT devices, but then also runs some things internally at our lab. And this is just kind of going through a handful of the nodes. This corresponds to the Nest, which, as you know, it does, or as you may or may not know, is for like home automation stuff for turning your AC on and off remotely. And the next one is the August. This is a lock that operates on Wi-Fi for some reason. This is the SmartThings connected hub. This has a variety of like low power Bluetooth and Zigbee devices that then connect to the hub, but the hub beacons. So this is a good example where if the device isn't using DNS, obviously I'm not going to be able to detect it automatically, but they often, in almost all cases at this point, have to connect to some kind of hub that's on your Wi-Fi network, and these have an update domain, these have a thing that they beacon out to that can be detected. And then at least you know where in the network, you're running Zigbee devices or Hue light bulbs, for example. Speaking of Hue light bulbs, here's a variety of domains for the Hue bridge specifically. I think the Hue light bulb is the most popular one at this point, but again, a bunch of these corresponding to that. Here's my iPhone that happens to also be running on this network. I want to point out that fourth from the bottom is that e.crashlytics.com domain again. So this is something that over time, you need to be regularly updating these models. This isn't something you can label once and then forget about, because new versions of operating systems come on all the time and new devices are going to be coming on all the time. So again, automation is key here. And next guy. And then I was also just exploring on Georgia Tech's network to try and find a variety of other devices. So here's a PlayStation 4 I found. Obviously, college campus, there are going to be a lot of these. Looks like there's about 38 of them, but it kind of hovers between 30 and 40 from what I found. Also, here's a variety of Xboxes, and then next we have a bunch of Nintendo Wiis. And that's mostly what I have for today. I'd be happy to take any questions, and thanks for listening, y'all. Well, I'll be around if you change your mind. Thanks.
Thanks, Yassine. Okay, so I'm Dwayne Wessels. I work for VeriSign, and next I'm going to tell you about our plans to increase the size of the root zone signing key. So here's some terms that are used throughout this presentation that you may or may not be familiar with. KSK is the key signing key, which is a function that's operated by ICANN and IANA. ZSK is the zone signing key, which is operated by my company, VeriSign. KSR stands for key signing request, and this is an XML bundle of keys and things that VeriSign sends to ICANN. It's a request for signatures, and the thing that comes back is SKR, as a signed key response. So you may have heard things about a KSK rollover, and that is not what I'm here to talk about. Actually, right after myself, Ed will talk about the KSK rollover, and we will both tell you that we're both working closely with each other on both of these projects to make sure that there's no interference or anything like that, and that everything's going to go smoothly. This table shows the current parameters for DNSSEC in the root zone. The algorithm for both keys is algorithm 8, which is RSA SHA-256. The size of the KSK is 2048, and the ZSK is 1024. And there's some other interesting data there. But just to point out here that the only thing that we're changing is the size of the ZSK, that none of the other parameters will be changing. This table shows some of the schedule for the ZSK change, and two of these things have already occurred. Back in April, we performed a bunch of testing between ICANN and VeriSign, and in May was the 25th KSK ceremony, at which the keys for Q3 of this year were signed. The next big event is the 26th ceremony, which will be in August. and we'll sign the keys for Q4. And then on September 20th is the date at which the larger key will become pre-published in the root zone. So that'll be an important milestone for us that we'll watch closely. And then on October 1st, which is the first day of the fourth quarter, is when the root zone will first be signed with the larger key. This chart shows the schedule graphically. It's divided into quarters. This is the year 2016 divided into quarters. And for the first 3 quarters, down at the bottom, you can see that the zone will be signed using 1024-bit keys. And in that last quarter is when it'll transition to a 2048-bit key. And above the bottom line, the top line shows when the key signing ceremonies occur. So those occur basically 1 quarter in advance. However, due to the need for this pre-published stuff, at the end of every quarter, there's a pre-publish period. And so in September, as I said, is when we will pre-publish the 2048-bit key, and the ceremony for that has already happened back in May. So if you don't already know, for the root zone, the zone signing key is rolled every quarter, and each quarter is divided into 9 slots of approximately 10 days each. Sometimes the 9th slot has to be a little bit longer because quarters are longer than 90 days. Every slot is when the DNS key RRSIG record changes. So you'll see the slots sort of prominently talked about here in this presentation. The pre-published key happens 1 slot before the end of a quarter, and the post-publish happens for 1 full slot after the start of a quarter. This chart sort of shows the slots at the top, although slots 2 through 8 are all combined together because they're all the same. But here you can see how the keys sort of overlap in slot 9 and slot 1. And those are the periods where, because there are 2 keys published, the size of the DNS key response is a little bit larger than normal. So this graphic actually shows things as they have been occurring for the last 6 years or so. This is the normal 1024 to 1024 rollover schedule. And when we transition to 2048, this is how it's going to look. It's very similar. In the middle here, the middle section represents Q4, which is when we have the larger key. And the one thing that's a little bit different is for this transition, we will have a longer post-publish period. So whereas normally slot 1 is the post-publish period, we're going to extend that for 3 slots to give ourselves a little bit extra wiggle room just in case we need it. That's basically what I just said. So I have some data on what it means to have a larger zone signing key, what it will look like in the zone and in the DNS traffic. So if you were here for Roland's talk yesterday, you heard some of this concerns about response sizes, and in particular the size of DNS key messages, and that's what this chart shows. There's a number of different configurations here, and they sort of go in order of how they will happen for the transition. At the top, we have a normal 1024-bit ZSK with just 1 key. And the next one shows a 1024 to 1024 rollover with 2 ZSKs shown in purple or dark blue. And the size of that response is 883, if my eyesight is correct here. When we do a 1024 to 2048 roll, that DNS key response size is going to go up to just over 1,000 bytes, 1,011. And then it'll go back down during the periods when we have just one 2048-bit ZSK. When we do a 2048 to 2048 roll, which will again happen every quarter from then on, that size will be, does that say 1139? And I think the two, I think these two graphs show, oh, this is the K, yeah. So the bottom one is what will happen during a KSK rollover. It'll be the same size, except during the KSK rollover, if there's a period where we're rolling the KSK at the same time as we're rolling the ZSK, then the response size goes up to 1,400 bytes. And at the time when there is a revoked KSK published, the response goes up to 1425 bytes. So that was all about the DNS key response size, but we also need to worry about the size of other responses. So to sort of help us understand this, we did some simulations. We captured some query logs from a root server and replayed them through name servers configured with various parameters. Took 10 minutes of data from a root and replayed those queries over both TCP and UDP, and then recorded the size of the responses and whether or not the name server returned a truncated flag and so on. So one of the first things that we looked at was fragmentation. How often was a UDP response fragmented in this configuration? And essentially it's 0. You can see some very small bars down there at the bottom. The only responses, root zone responses that need to be fragmented are responses to any queries. And in this trace data, there were very few any queries, something like 10 or so. So essentially it's 0 apart from the any queries. Now if we look at truncation for, so that was fragmentation. If we look at now truncation for DNS key responses, remember truncation can depend on the advertised buffer size in an eDNS option. So there, some clients may have different values there, and this shows that where we are today, the green all the way over on the left, we have about 2.5% of all DNS key responses experience truncation. But when we switch to 2048, that's going to jump up to 5.5%, so more than double. Oops. That was for DNS key, and this is the same for all queries. So in this case, the only thing that it depends on is the size of the zone signing key. When we start signing with the larger key, then the overall truncation will go from about 0.5% to about 1.4%. This graph shows the size distribution of responses. And again, here the only thing it depends on is the size of the key used for signing. The red on the left shows the sort of the current situation with the smaller key, and the blue shows the distribution for the larger key. This chart shows the amount of bandwidth that a root server could expect to deliver under both scenarios. And this is for a letter as a whole. Of course, as everybody probably knows, root servers are widely distributed, so this is not per server, this is per letter in aggregate. And based on our simulation, today we're at something like 250 megabits per second of traffic with a 1024-bit key. And when we change that to a 2048-bit key, that's going to jump up to about 300 or 350 megabits per second. So that's a pretty significant increase. We'll talk a little bit about the fallback plan. So while we fully expect everything to go smoothly, prudence dictates that we be prepared to execute a fallback plan if there are unforeseen problems that occur. So one key aspect of our plan is that if it becomes necessary to fall back to a smaller key size, that we will be using the exact same key that was used in the previous quarter. So in order to support that, we are submitting 2 KSRs to ICANN to be signed at 2 of the ceremonies. One of those ceremonies has already happened. The next one will happen in August. Here's briefly some criteria for executing a fallback. It would have to be something obviously unforeseen, something very serious, and something that cannot be solved by temporarily disabling DNSSEC validation at a small number of recursive name servers. As I talked about before, some of the important milestones are at the time when we first pre-publish that larger key. That happens in September in slot 9, and then the following slot when the zone is signed with the 2048-bit key. And then after that, after we see the first signatures from that key, it'll take a while for the old signatures to expire over the course of a couple days. So we'll be watching that closely. And then the last important milestone is when we finally remove that old 1024-bit key at the end of its 3-slot post-publish period. That's our point of no return, which we're committed to continuing with the 2048-bit key. So this chart shows two sort of timelines. At the top shows the normal sequence where we do the transition from 1024 to 2048. And the bottom shows our fallback options. And you can see, I don't know if I have a pointer, but you can see that here in this quarter we've got this blue key, and in the fallback the blue key extends for 2 quarters because we'll be reusing the same key there as the fallback. If we need to fall back in slot 9, it's pretty simple. We just remove the new key from the zone and cease publishing with it, and then we would never sign with it in the next quarter. That's what that says. If we need to do a fallback in slot 1, it's a little bit trickier, but since the old key is still being post-published, we can revert to signing with the older key, with the smaller key, and then remove the newer key as dictated by the particular circumstances. That's basically what that says. So lastly, I want to encourage everyone to test their networks. We've developed a tool that you can use to test your network's ability to receive larger responses. There's this domain called keysizetest.verisignlabs.com. And if you go there, you should see something that looks like this. It will do queries using JavaScript to a number of domains and tell you if it was able to retrieve them or not. And you should see mostly green. Well, there's a test at the bottom that should fail. The red should be there. And if you go there and if you see something different than this, then I would very much like to know so we can help you understand what may be the cause of it. So that's my presentation, and I'm happy to take questions for a few minutes if there are any.
Hi, Dwayne. Matt Petak from Yahoo. So you kind of postulated a slightly binary condition here at the yay, everything went well, we get rid of the 1024-bit key at slot 3 and life is happy, or boo, things didn't go well, we continue using the 1024-bit key, we phase out the 2048-bit key, and we scratch our heads. And in your picture, you sort of said, and in the next quarter, we do the 2048-bit thing because everything's good. Failures in this sort of scenario are seldom black and white like that. So if you what's your criteria? At what point do you decide, well, we broke some stuff on the internet. Is enough stuff broken that we plow forward and we just say, hey, 20% of you are screwed, but it's okay, we'll jettison 20% of the internet? Or do you say, if 1% breakage happens, we roll back? What's your criteria there that says how broken is it before you say we got to roll back?
So we don't have exact numbers of percentages, but I think it's going to be a judgment call depending on what we know about the severity of the problem. If it's 20%, I think that would be severe enough to do a fallback. If it's 1%, and if that 1% can't be fixed easily or worked around easily, then that's a tougher judgment call we'd have to make, and that's a judgment that we'll make together with our partners at ICANN and VeriSign to make that decision. So.
If we're part of the 1%, is there an address we reach out to, or do we just jump up and down and scream really loudly on every mailing list we can find?
So we'll be doing some more outreach. There will be an address. It'll very likely be the standard VeriSign customer service address. We'll also be, taking advantage of Twitter and things like that. So we'll be posting some messages on the various mailing lists with contact information. And of course, anyone in the room here or watching would know my address, and so all those will work. Yeah.
Email Dwayne. Put it back. It hurts.
I can assure you that I probably won't be sleeping for a few days around these dates. So.
Hi, Roland Freshwick, SurfNet. In the measurements, did you differentiate between IPv4 and IPv6? Because I couldn't find that in the slides, and I was wondering whether. I was surprised that you see so little fragmentation, because I'd expect to see some more on IPv6, because some of the really large responses exceed the minimum MTU for v6.
I'll have to go back and look at my code. I don't remember. I think I did, but I'm not 100% confident. So
okay.
I need to go back and look at my scripts and see.
Yeah, because this is something where it's like meddling middle boxes can bite you, because if something goes wrong with ICMP-v6, your stack might fall back to 1280, and we see that quite a lot for DNS. And then if you have responses that are, say, the exceptions, right, the ones where you either retract the KSK or where you roll the KSK and ZSK at the same time, you'd be exceeding that MTU, and you'd be, I'd expect to see more fragmentation on
Right. So.
v6.
And to be clear about like this graph, the simulations that I did, this is not including a KSK roll. This is just for the ZSK.
Okay.
Okay. So you're when you talk about 1280, you're
Yeah, that's out of scope here. Yeah.
yeah you're sort of way up there, up on the right. But yeah, I'll take a look at my scripts and get
Thanks.
back to you. Yeah. Okay, thanks. So I think we're in good shape. We've got time for Ed to talk to us next about something even more exciting for the root zone.
Hello, my name is Ed Lewis from ICANN, and along with Dwayne and the folks at VeriSign, we manage what goes on DNSSEC in the root zone. So I'm going to cover three main topics here. A little bit about root zone DNSSEC operations, just so you're familiar why Dwayne and I are giving separate talks about something so similar. The next part of this is the dates at which we intend to make changes to the root zone on our end. And then activities that are going to happen up and through those dates that involve things that we're going to do on the ICANN side and things that you're going to do on your side if you're doing DNSSEC validation. So DNSSEC in the root zone right now, it's managed jointly between ICANN and VeriSign. I'm pretty much probably aware of that by now. ICANN is the IANA functions operator from a contract from the NTIA. VeriSign has a cooperative agreement with the NTIA, and so we're separate organizations working together to manage the root zone. Now, DNSSEC key management, maybe you probably know this, that we have two cryptographic roles, key signing keys, zone signing key. They're important in signing, and the important thing here is that these two roles are separate and operate separately in the root zone. At ICANN, we manage the KSK. We have the KSK private key in one of our devices somewhere. We open it up, use it sometimes, we close it back up. VeriSign is in charge of the ZSK, and they have it in their secret devices somewhere, wherever they do their work, and they operate it on a more frequent basis. So these two pieces of data, these two configuration parameters for the internet, are operated by different organizations, but we work together with this. Underway right now, the ZSK will be lengthened. You just heard about that. And the KSK will be changed. These two activities are separate. but they're coordinated because one has to happen before the other one starts. And also what happens in the first one will impact what happens in the second one. One of the common questions are, why change the KSK? This is just about the KSK now for the rest of the talk. The KSK out there, it has no expiration date. There's no signs of distress, no weakness in it. On the other hand, nothing that's secret can last forever. It's not good to not change a secret at all. It's bad practice to assume that this secret will be secret forever into the future. So we're going to have to change it at some point. We don't know when or why we have to or forced to change it, but we want to make sure we can do it when we don't have a problem. We want to do this in normal conditions, so everything else is working fine. We're going to go through the actions of changing this. The big challenge here is that it's very easy to change the private side of this, the private key. It's a few HSM commands, and we go from one to the other. It's pretty easy. The hard part is that the public key is a configured parameter in everybody else who is doing DNSSEC validation in their machines, something we can't measure. We don't even know who they are. We can't measure it. We can't get in there. We certainly can't make the changes. So we're talking about an action where we have to do something on the ICANN side, changing one parameter, and everyone else has to follow along. And we don't want to do something, ICANN doesn't want to do something that's going to hurt anybody else out there. We can't do this in a test environment either. There's no test environment that can counter all of the actions out there. Anytime we find someone who's aware of what we're doing, they're already no longer the problem because they're going to follow along. It's the people that don't know about this need to be told about this somehow. And so we're just trying to make sure that everything's clear for this to go out there. So this is the slide which is going to probably get more of the attention from the operators in the group. In the room. Assuming the ZSK lengthening progresses to its plan, assuming there's no delay in that, because of course, if for some reason the fallback happens in the ZSK, whatever causes that's probably going to be a problem for the KSK also, so we're not going to make any promises that we're going to go ahead anyway. We really want to know why something happens. Is it something in the protocol? Is it something that some people just didn't catch up? These things we have to figure out first. We have a plan in progress. The publicly viewable version of the plan will be available next month in July, sometime early in the month. This plan is being built upon work done by a design team of public people last year. There were comment periods in the past on this. So this time we're going to go out there and just have the plan on view. Ceremonies will be coming up. Dwayne talked about the KSK ceremonies. They happen every quarter, approximately every 90 days. In October and November of this year, 2016, we will, if all goes to plan, we will make the key. We'll make the key in one of our facilities, and 3 months later, we will take that key and put it into the other facility. At that point, it'll be ready for operations. It'll be in all of the devices out there, so for availability, resiliency, and all that, we've met those benchmarks. At that point, the key becomes something that it's coming at this point. We know what it is, and we can tell everybody what it's going to be. In the DNS, what you'll see about regarding the KSK role is on July 11th is when you should see the new KSK appear as a DNS key record in the Apex DNS key set. The significance of the 11th is that that's 10 days after the quarter starts on July 1st. And as Dwayne was talking about earlier, we have 10-day slots for the ZSK management. 10 days into that quarter, the ZSK is post-published for the previous quarter. When it gets pulled out, we'll throw in the KSK at that time. And there should be no change in the size of the DNS key response because of the ZSK being the same size at this point, if everything goes well. 3 months later, October 11th, we're going to start signing the DNS key set with the KSK. This is the day that things will really come to a point of concern. On that day, the new signers out there, if people have not configured the new trust anchor in their machines, they won't get anywhere on the internet. So up until then, we want to make sure everyone knows about it, has it configured, done correctly, and so on. 3 months after that happens, we're going to begin the process of revoking the KSK and revoking in the sense of what is defined in RFC 5011, the automated updates of DNSSEC trust anchors. So upcoming on our end, we're presenting the plan is going to be our next concern, which will start in July and go through the end of the year, roughly. We're going to try to reach as many different regions of the world, go around to different operator groups and say, here's what we're planning to do so you can be prepared for it. We're working with different groups of people to make sure that the software out there that's available, tools are prepared for the change. Once we get into January, when the new key is available, we will switch to talking about the new key. We will have the key and want to make sure that you know this is the key. The key will be available, we'll be talking about it for a while before it actually gets into the DNS later in the year, and also available through a website. And in the middle, and next year, from July onward, we'll be following the protocol that's defined in the automated updates of DNS like trust anchors, otherwise known as RC 5011, which says basically we will put the new key in as a key record. It'll be there for at least 30 days. In our case, it'll be for a quarter. Everyone can then adopt it when they see it's been there long enough, and then go through to the revocation phase. If you don't follow 5011, that's fine. 5011 is what we promised to do. You don't have to follow along with it. Now, trust anchors, changing trust anchors is a job not for ICANN, it's for you. Anyone who's doing DSX validation, you manage your trust anchors. If you use the automated updates, this should work automatically. We've tested software out there. The software products that most people are using have 5011 support in it, and that seems to work pretty good. However, if you decide not to use that, and there are many reasons not to use that because you like configuration management to be centralized, which is much more common, you will have to do something more manual. You have to have knock tickets, some things out there. So long as you're aware of what you're doing, you'll be fine. And aware of what you're doing means understanding what a trust anchor means, what it means to look at the keys, to examine the keys. Some people like to have multiple copies of the keys and put them on the desk and make sure they're all the same before they go ahead and run with it. You'll have to, if you're doing that, you'll have to be doing that by October 11th of next year. And that's where we have to make sure people are prepared and have the background and the knowledge to do this on their end of the system. Right now for testing, we have a couple of test environments out there which actually exercise ROC 5011. They speed up the clock because waiting 30 days for the add hold down time in the RFC is kind of long, and operators we shouldn't have that amount of patience. They speed the clock up to us much more frequently. And so these two URLs I have up there, they're tuned more towards those who are developing tools or those who are willing to change parameters in your code that really aren't supposed to be out there to be changed. For example, bind code can work with this, but you need a secret undocumented runtime parameter to catch up. And if you want that, you can ask about it, but it's not meant to be used in operations in any way. Unbound also has a trick for doing this too, a little bit more obvious, but this shouldn't be obvious to do this, but it's more obvious. The first URL there really mimics what ICANN is going to do. It has the trust anchors that Diana's putting through the website out there. The second URL is following 5011 in more of a pure form. It's just doing a 5011 test out there. Now, we recognize that these aren't the best resources for operators who don't want to meddle with some of the configuration parameters. It's not good to do that. We will have something more suitable for that forthcoming in the next couple of months. For more information on this, we have a mailing list up on top, KSK rollover. We have a Twitter feed, of course, a hashtag #KeyRoll, and we have a web page linked off of the ICANN.org webpage about the KSK rollout there. You can go to these places for information. You can contact anyone you know that's involved with this process. And the promise to have the plan available next month and go on, and we'll talk about some more. I don't want to get into too much detail now because the plan, I want to wait till the plan is actually what we publish for people to look at. And so, to conclude, the usual tail slide for an ICANN presentation, and I'm ready for questions. Oh, good, done. Oh, sorry.
Matt Petak, Yahoo. I do applaud that we are doing this first ever, gosh, it should work, but let's make sure it actually works exercise. I will note that if I read that correctly, this is an almost 2-year process cycle we're talking about. I understand we are proceeding with extreme caution here. Is the expectation that if this goes smoothly, future KSK rollovers could be done in a slightly more accelerated time frame?
Maybe not that accelerated. Let me explain. The reason why it takes so long is that we're fitting this into the existing institutional practice of managing the key. And because of that, we do things on a quarterly basis for the KSK. We could sped this up by having special ceremonies at extra cost. So that's actually why it's taking longer. What you'll see on your end, you'll see basically a change over 3 quarters. Although we have a much longer plan because they include making the key, carrying it across. You wouldn't see that. We could also pipeline that, so we may do that for the next one before we're done.
Well, I guess the concern here is you say there hasn't been a weakness found. That's no weakness that we're aware of.
Right.
If at some point a weakness is discovered, perhaps in the new key, and we have to do this in more of a hurry, telling people, we have a weak key, we are concerned, give us a year and we'll have a new one, doesn't.
Yeah, okay. Yeah, I'll tell you, the biggest reason for the long time frame, one is that we're minimizing cost, right? And that has to do with the ceremonies and all that. The biggest, I guess in terms of the schedule, the critical path item, whatever, I can't think of the word, but what's causing this to be long is the 30-day add hold timer in ROC 5011. I don't think we can twiddle with that in any way. We could accelerate the quarters to be more quickly, but then we'd have to change a lot of our institutional practices around that, and we're trying to minimize that for a couple of reasons. And it's basically that, do we want to, we'd have to juggle more operational unknowns to speed it up, but there's no apparent necessity. In this case, certainly we don't need to.
But if there was a more critical situation where you said, wow, we actually do have a weakness, then we could go down to that 30-day and speed up the cycle.
It's a cost versus budget thing. The cost of doing a ceremony is this. The value of it depends on, is it urgent or is it not? So I think that would tip it whether we have more frequent updates to this.
Gotcha. Okay, thank you.
Sure.
So thank you, Ed. This concludes the DNS track. Thanks, everyone.